Hi, welcome back. So, we last spoke about the rate equation approach. This should read rate. And took some examples from biomolecular systems, like the transition from 13 cis to all trans retinal, which is involved in vision, enzyme substrate kinetics beyond Michaelis Menten, which we did not write down any equations for. And finally, we concluded that cytoskeletal dynamics proves to be a more interesting phenomenon simply because it goes beyond what you have already studied and something hopefully that might be a little new for you. Okay. So for today, for this particular module, and I'm referring to as part 2 of the cytoskeletal dynamics part, we're going to talk about a simple model of polymerization dynamics, which involves making some simplifications with respect to the nature of the polymer, its addition and removal, and yet strangely we get some very exciting and useful results from it. And those two results that I'm going to discuss for this particular part are the distribution of the lengths and the mean values of the lengths, and we'll use the expression that we get from it to actually calculate the mean lengths of actin. So let's get to it. So what is this simple model that I've been referring to? Now, what you should notice here is that I have modeled my polymer, despite what I said earlier, like as a line of bricks, these boxes. These boxes are formed into a sort of linear array. They only seem to grow from the ends. The end growth is itself dependent on two rate constants, K on and K off. These K on and K off rates are identical at both ends. In other words, there is no difference between the ends. You can say there's no kinetic polarity. And that this dynamics gives rise to a distribution of polymers, which we're going to try and make some sense of. So Pn at time t is the polymer of length n in terms of monomer units at time t, n being the length of the polymer in terms of number of monomers, t being the time. In that case, Nn is the number of filaments of length n, and L averaged is the mean length of the polymers. So what is the equilibrium length distribution like? So at equilibrium, we expect this reaction, that is to say, for an n-sized monomer, the addition of, n-sized polymer, the addition of a monomer results in growth by 1 unit. This is n plus 1. This is reversible and it is governed according to how we have written it by a dissociation constant. This dissociation constant Kd by definition is the dissociation of Pn plus 1. Therefore, it can be defined as Pn times P1 upon Pn plus 1. Yeah, that's by definition. If we assume that Kd does not change no matter whether you have a you have n is equal to, if you have just 2 or 5 or 10 monomers in the filament, it should not matter. This is 1, 2, 3, 4, 5, 6, 7, 8. I'm running out of space. 9, 10. This is another way of saying that the rate constant of growth does not depend on the length of the filament. And we will return to this kind of a question a little later because there are some interesting exceptions to this. But for generality and for simplicity, this is a reasonable assumption. So we take a few cases, P1, P2, Pn, and we ask what are the expressions that we can determine for their population. So N1 gives Kd is P1 times P1 upon P2, which is P1 square by P2, which is kind of self-evident to most of you. Yeah, this was our polymer. These were the two precursors. We can therefore change the signs and write the P2 in terms of P1 square by Kd. So now you get the picture for an N2, N is equal to 2 dimer, Kd is P2 times P1 upon P3. But if we substitute the value of P2 in this expression where we have shifted P3 on the left hand side, then we get back P3 is equal to P1 cube to the divided by Kd to the power 2. In other words, this P1 cube is nothing but the monomer concentration raised to the power, which is the same as the size of the number of monomers in the filament. Therefore, it looks like we can generally write P of n concentration, meaning how often it is prevalent. If the volume is constant, it's just a number of filaments of a certain length is equal to P1 to the power n upon Kd upon n minus 1. And if you take Kd out, because we'll see it becomes a little more useful, then we get Kd times P1 upon Kd time to the power n. Writing this in the exponential form then becomes Pn concentration, meaning to say the number of filaments of a certain length n is equal to Kd e to the power n times natural log of P1 upon Kd. This is coming from this very general idea that e to the power natural log of some x is equal to x. So, what this allows us to do is, number one, write this in terms of a symbol which we are using here to label this equation number 6, which is P of n is equal to Kd into e to the power minus alpha n. What is alpha? Alpha is minus natural log of P1 by Kd. We just basically substituted this term here, P1 by Kd natural log, by a term alpha. We created a new term. The negative signs cancel out, it becomes plus. But the nice part about this is, just stare at this equation for a while and just think of it, that as the the x variable, in this case n, increases, the number of monomers in the filament, or the length of the filament you may say, we see a characteristic dependence, which is an exponential decay, coming out of this equation number 6 of the number of filaments. In other words, nothing but what we always like to talk about as the frequency distribution of filament lengths. So can we graph this? Sure, and here it is. So our graph of the frequency distribution of lengths looks like this. It is the red line, e to the power minus alpha n, and alpha is itself given as this expression here, minus natural log of P1 by Kd. So does this have anything to do with any experimental reality? Can we go back and check, and so on and so forth? Because we made a lot of gross simplifications. So it turns out cytoskeleton filaments and their polymerization have a functional role, and their length distribution has a functional role. And the most prominent place where this happens is the brain. And in particularly in humans, it has been shown that tubulin B, one of the monomers that makes up the tubulin dimer, tub B3, which is an isomer of tubulin B, when it is missing, results in malformation of corpus callosum axons and the oculomotor nerves, leading to mental defects and vision defects. And ironically, this comes down to the level of the cytoskeletal filaments, where the dynamics of the mutant tubulin are altered as compared to the wild type. And the consequences of this are the ones that then seem to appear to show up in brain defects. What is interesting to note is that not all tubulin Bs were mutated, just tub B3. And this is also not homozygous but heterozygous. Already this causes problems. But what about the lengths? So when in our lab we did some experiments where we assembled tubulin from brains, not human, goats, because that's the easiest large mammal that we can get hold of, and analyzed the filament lengths made by stabilization. Lo and behold, we actually get very nice distributions. What is the difference between left and right, you may ask? Well, on the left are the filaments that were assembled, and on the right are the same filaments after passing through a syringe and pumping it up and down by a process called shearing. In other words, we basically broke the filaments. So when we do that, we obviously expect a reduction in length, and you see that in the exponential fit with the 1 by lambda in the exponent indicative of the approximate mean length that you can get from it. This is 4.81, this is 2.33 after shearing. So indeed, length distributions from experiments seem to fit our theory. What about means? Well, it's fairly straightforward. If you want the mean of something, then you need to take the frequency of the weighted lengths and divide it by the number of filaments. That's what the average means. So to do that, we need to integrate from overall lengths by n, which is the length of that, the weight of that filaments, yes, the weight of that distribution times e to the power minus alpha n, and divided just simply by the frequency, summed over all lengths. And this leaves us with this expression here, which is 1 upon a natural log of kd by p1. Please note that the numerator and denominator in the brackets have shifted a little bit. And graphically, this looks like this. That is to say, as the monomer concentration increases, the mean length increases. This is not very surprising. But how exactly it increases is given by our nice little expression here, which is 1 by alpha. So can we put in some real numbers and try to make sense of this? Well, sure. So let's put in some real numbers. And this is the last part of this module, which is our sum. So we're going to take actin, which again we say can behave as a symmetric polymer for this assumption, where growth and shrinkage happens at both ends by the addition of monomers into the lattice, and the K off is measured to be 10 per micromolar per second, and K on is 1 per second. This of course means Kd is nothing but K off by K on, which is 0.1 micromolar in units. Just please note how we got to that point in terms of the units. And then substituting into our expression one average of n, that is to say the mean length in terms of monomers, is 1 by alpha. We write down kd by p1 natural log in the denominator, which if we take in the numerator, we get natural log of p1 by kd. So what is the actin in vivo concentration? Well, reports tell us that in cells like yeast and mammalian cells, it's around 50 micromolar. So when we substitute all the numbers now, we get 50 by 0.1, 500 natural log, that is 6.2146 in terms of monomer units. So, but can we get absolute lengths? Well, subunit size is of actin is 5 nanometers for G actin. So when we now multiply this, we get 31 nanometers as the average length. Uh, it's important to note that for so-called self-assembled polymers like these, the value of the Kd is also referred to as the critical concentration. This critical concentration we'll see has an interesting role to play. Suffice to say, for the moment, we will just simply state that the monomer concentration, if it is less than the critical concentration, leads to net shrinkage, while if it is greater than the critical concentration, leads to net growth. So for the next part of this module, I'm going to talk about length fluctuations, filament dynamics, treadmilling, and some